Okay, let's stop and take stock of where we are right now. You know all about atoms at this point. You know how they're put together, their protons, neutrons, electrons. You get how the electrons are arranged in these energy levels around the atom. You understand that there is this concept of valence electrons, or those ones that are on the outermost energy level. And we have been able to express those by these Lewis dot diagrams. And I said that last week that this was going to get to be very important, and that we need to look at an atom on the periodic table and be able to identify how many valence electrons does it have. Well, this is where we're starting today. Now, instead of just looking at atoms today, we are going to start looking at compounds and how are they formed and why are they formed. Now, when we say compounds, let's actually give ourselves a definition here. A compound is two or more atoms chemically combined or stuck to one another. And you guys already know that atoms do this. You're very familiar with some compounds. You know that H2O is water. That's a chemical compound. Now, you know that water is not just hydrogen and oxygen thrown together in a bowl and just kind of mixed up, just hanging out together. And you also know that H2O is never H3O. That's not how the compound works. We know that water is hydrogen and oxygen, and it's always two hydrogens for every one oxygen. This is an example of a compound. It's two or more atoms that are chemically combined. There's some more specifics that we're going to note with this, talking about how compounds always have the same ratios, are always put together the same way, so forth and so on. But for now, let's start off very basic, that a compound is two or more atoms that chemically come together. They stick to one another. Now the question is, why? Why do these atoms come together and stick to one another? What good does it do them? Okay, I'm going to reference the periodic table. And we've talked about valence electrons. And we can now look at the periodic table and determine how many valence electrons any particular atom has. We know that, and I'm going to write VE. That group there has one valence electron. That has two valence electrons. That everybody in there has two valence electrons, because remember, the next electron starts going into the D sublevel, which is not the outermost energy level. 3, 4, 5, 6, 7, 8 valence electrons. So we can now look at the periodic table. We know how many valence electrons each atom has. We know that no atom has more than 8 valence electrons. That's the most you can have, because once you get to here, if you add another electron, well, then you go to the next highest energy level and we start all over again. So that number 8 is going to be important for us, because there's a term here, another one of those chemical rules, called the Octet Rule. Well, what a rule is. A rule is something you got to follow, and this is something that atoms do follow. I'm going to simplify this for you. It's not going to be necessarily the most sciencey sounding definition, but it will work for us. All atoms want to have 8 valence electrons. Now, the reason this is that atoms are actually most stable when they have 8 valence electrons. Remember how we talked about when you had these orbital diagrams like this, and we had something like this going on. When you have a situation like this, remember that these electrons are constantly moving around because it's not full. Well, these two guys decide they have to share an orbital, but these two guys get an orbital to themselves. That's not very fair. So the atom pushes this electron, remember, because they're both negative. So this electron will get pushed into that orbital, and these guys will share for a little while. Well, and then that electron will get pushed there and share for a little while. So this kind of oddball electron keeps getting pushed around the different orbitals. And that's a lot of movement going on. That's a lot of stuff happening. And it's not very stable because things are constantly changing, and atoms want to be stable. We want our electrons to be as stationary as possible. So the octet rule, if you end up having 8 valence electrons, and I'll do, let's say this is 2s2, and this is 2p6. Well, now everybody's full. And now we can't have any of these electrons bouncing around from orbital to orbital because there is no room anymore. So this is the most stable. And that's what atoms want to be. They want to be stable. They don't want stuff constantly moving all over the place. So atoms are shooting for having 8 valence electrons because that makes them the most stable. Well, not all atoms have 8 valence electrons to start with. These guys here, these guys do have 8 valence electrons. That means this group, the group 18, what we call the noble gases, are stable. Meaning these guys don't do a whole lot. They're already fat, dumb, and happy atoms. These guys have made their goal. They are happy electrons, or happy atoms, because they've got their 8 valence electrons. Nobody else on the periodic table starts off with 8. So they have to work at it. And they are shooting to get to 8 valence electrons. Now, how does this happen? If you only have 7, how do you get to 8? Well, what happens is you have to go and you have to get an electron from somebody else, from somebody who wants to give one up. And we had a term for that. That is related to the term electronegativity and electron affinity. So electron affinity and electronegativity basically describe, well, are you going to take electrons, and how easily do you take electrons? Well, fluorine, think about fluorine. And we said with electronegativity, it gets bigger as you go this way and bigger as you go this way. So fluorine is very, very strong at taking electrons. And look at the reason why. Because fluorine's really close to the goal of getting 8, which makes fluorine really, really motivated to get an electron. We say it has a high electron affinity. So fluorine is going to take electrons from other people. Taking an electron makes you become an ion because now you're not neutral anymore. You have a charge. When fluorine takes 1 electron, it becomes an ion with a -1 charge. Now, oxygen has to take 2 electrons to get to 8. So taking 2 electrons, it would have a -2 charge. Nitrogen would have to take 3, so its ion would be a -3 charge ion. Now, we're going to stay away from this column here for a second because, wow, 4 is only halfway to 8. So we'll pause and come back to him. Let's go over here. This column here, they only have one valence electron. To get to 8, they would have to take 7 electrons from somebody else. Now think about that. That would mean you would have to gain 7 negative charges. And the more negative you become, the harder it is to attract more electrons. Besides, who are you going to take electrons from? Oh, I could take 7 from fluorine, right? But remember, fluorine doesn't give up electrons. It has a very high electronegativity. Fluorine holds electrons very tightly. We know the elements over here do not hold their electrons very tightly. These are the ones that will give them up pretty easily. So let's consider sodium. Sodium would be a 3s1. Has 1 valence electron, can't possibly take 7. But in the previous energy level for sodium, so here we got sodium with its first energy level, second energy level, third energy level, has 1 valence electron. In the second energy level, sodium's got 6 electrons in here. So think about it this way. Sodium lets this electron go. And we know that about elements on that side of the periodic table. They don't want to hold on to electrons. They give them up pretty easy. Now, if we think about sodium, the sodium ions now has only 2 energy levels. And, there's 8. Because it's 2 and 6 makes 8 electrons in there. If we get rid of this one, now sodium only has 2 energy levels, and that second energy level has 8 valence electrons. And 8 valence electrons make sodium happy because it satisfies the octet rule. Sodium can't take 7 electrons to get there. Its best option is, hey, let me get rid of this one, and then it's like I have 8 valence. So what sodium does is it gives up an electron. By giving up an electron, it becomes an ion, but it becomes a positive ion. Sodium's charge would be +1 because now it has 1 more proton than it does electrons. So we come back to the periodic table. Sodium, this column here, is a +1 ion. We should start to see a pattern. Calcium would be a +2 ion. Seems like all of these guys are going to be +2, but we'll talk about these a little bit more later. +3, because aluminum, boron, gallium, it's a lot easier for these guys to give up 3 to satisfy the octet rule than it is to take 5. And like I said, we'll come back to this column here because they're kind of in the middle. 4, what do we do with 4? Is it easier to give up 4 or to take 4? Well, we'll come back to that later. All right, so now we see how atoms can help each other out. If we think about it this way, oxygen wants to gain 2 electrons. Pick a guy over here that wants to give up 2 electrons. Calcium and oxygen can hook up and say, hey, look, dude, I want to get rid of 2 electrons. Hey, I want to take electrons. They can get together and help each other satisfy the octet rule. We'll start off with a very, very common combination of sodium and chlorine. Sodium wants to give up 1 electron. Chlorine wants to take 1. So let's look at sodium with its 1 valence electron, chlorine with its 7. All right, so these guys are walking down the street, and sodium's really trying to get rid of that electron. And sodium bumps into chlorine and says, hey, dude, can you help me out? I want to get rid of this electron. And chlorine's like, heck yeah, man, I need one more to satisfy the octet rule. So here's what happens. Sodium just gives it up. Says, hey, dude, there you go. Take my electron, please. Chlorine is happy. Sodium's happy. Everybody's satisfied the octet rule. We're good. So why doesn't sodium say, hey, appreciate the help, and then go about his merry way? And chlorine said, see you later. We're all good. Catch you in a later life, and go on its merry way. The trick here is now that sodium has given up the electron, it has a positive 1 charge. Now that chlorine has taken the electron, it now has a negative 1 charge. Positive and negative things attract. So now sodium and chlorine are stuck together because just like two ends of differently charged magnets, got a plus 1 and a minus 1, and we wind up with not a sodium by itself, not a chlorine by itself. We wind up with 1 sodium stuck to 1 chlorine. Hopefully you recognize that as what we commonly call salt. Sodium chloride is table salt. Very common compound. Works very well. There's a lot of salt out there in the world. And you can see why, because sodium and chlorine can help each other out real easily. And when they do, they become stuck together, and this becomes what we call an ionic compound. Ionic, ions, charged. An ionic compound, it forms when you have opposite charges causing the atoms to stick together. This happens when electrons are given and taken. Because now you have charge, you have ions, and you stick together because opposites attract. Now, you guys know the name of this. You know that's sodium chloride. I just said it. All right, so let's talk about how we name ionic compounds. First thing you do, is you say the name of the first atom. First atom was sodium. I said sodium. We don't say sodium chlorine. We say sodium chloride. So you're going to change the ending of the second atom to IDE. So you say sodium chloride. We'll do a little bit of practice now where I'm going to give you some formulas, and all you're going to do is you're going to use the periodic table and practice writing the names from the formula. Sodium chloride. Say the name of the first one, change the ending of the second one to IDE.